Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. My name is Sonia Olaoluwa and I'll be guiding you through physics. Today we'll be considering current electricity and we'll look at the definitions of electric current, potential difference and resistor. We'll also look at the Ohm's law before we'll consider the resistance in series and parallel, after which we'll talk about electric cells and production of current. Then we'll look at arrangement of cells in circuits, and finally electrical energy and power. Let's begin. In the previous class we talked about electrostatics, that is stationary charges, and we looked at how the calculations involved there. But I remember stating it categorically the other time, that it is all about static electricity. This time around we're looking at charges in motion, and that's what brings us to the matter of current. What is electric current? Electric current is the time rate of flow of electric charge. That can be represented mathematically by the expression I equals Q over T. Now, electric current is measured in amperes, and it can be the amperes is represented with the alphabet A. That's the symbol, the unit symbol. Of course, current is indicated with I, and charge is indicated with Q. Time is represented with T. We can measure electric current using a galvanometer or an amp meter. Let's talk about potential difference. What is potential difference? When electricity flows through a particular body, a particular conductor or a body, the amount of work that is done is what is compared to the charge flowing, is what is described as potential difference. Potential difference is also called voltage or voltage drop. So potential difference, that's V, equals amount of energy as charge flow. Potential difference is the amount of work done or energy used up as charges flow. So 1 volt actually equals energy or work done, energy used up or work done, that's in joules, divided by coulombs, which is the charge. So let's talk about it's measured in volts, and it is measured using a voltmeter. What are resistors? Anything that prevents the flow of current, the free flow of current in a particular circuit, is known as a resistor. Any kind of opposition to the flow of current is described as a resistor. It can come in different forms as resistance, capacitance, or inductance. I will consider that in future topics. It is represented with R and it is measured in ohms, which uses the symbol omega. And that takes us to the Ohm's law. Ohm's law states that when electric current is flowing through a circuit at constant temperature and pressure, if all things being equal, the potential difference is proportional to the current flowing through it. This suggests that I is proportional to V. Well, this proportionality, when we solve it, it results into I equals kV, and this K is identified, the constant is identified as the resistance of the circuit. Thus, we would have this kind of expression, but for simplicity's sake, we choose to take our R to the other side, and we'll have the expression V equals IR. And that is the Ohm's law. Now, the Ohm's law is limited to conditions where the nature of the conductor is not tampered with and temperature remains constant. Atmospheric pressure remains constant. All these things, changes in weather, changes in atmospheric pressure, temperature, can actually influence this particular expression. It can prevent it from holding. This is the limitation of the Ohm's law. Resistance in series. There are two ways in which appliances can be connected to each other. They can be connected either in series or in parallel. The expression up here, the diagram up here, shows two resistors connected together in series, in a series connection. Now, what happens is this: when electric current flows through the circuit. When it enters into the circuit at this point, it will run through R1, then run through R2, and come out. If there is a break in transmission somewhere in between, it would not get to the end point of the whole system. Now, in resistors in series connection, for us to calculate what is a total resistance experienced against the flow of this current, it can be calculated as R total equals R1 plus R2. But in parallel connections, as we have in this other expression down here, in this diagram down here, we see the two resistors and they are like bridged together, connected to each other, and then the current is being supplied in between them. Now, the currents can flow into this and can flow into this. So in this particular condition, if one of the resistors is cut off, the other one would remain unaffected. But the expression for calculating the total resistance that is experienced against the flow of this current is 1 over RT equals 1 over R1 plus 1 over R2. Let's take an example of each condition. Let's take this example. For our connection in series, our R1 equals to 5 ohms, while our R2 equals to 10 ohms. Our total resistance, as given by the expression, should be R1 plus R2. Thus, our total resistance would be 5 ohms plus 10 ohms. And our total resistance therefore would be 15 ohms. But if it were to be a parallel connection, using the same parameters, we have our R1 as 5 ohms and our R2 as 10 ohms. Remember, the formula here is different. That's RT equals 1 over RT rather equals 1 over R1 plus 1 over R2. So 1 over RT would be 1 over 5 plus 1 over 10. This would give 10, and we'll have 2 plus 1, which equals 3 over 10. So our RT would be the reciprocal, that's 10 over 3, which would be 3.33 ohms. Which would be 3.33 ohms. Now, if you observe, when it's in a series connection, the amount of resistance is higher when the resistors are higher. But in this parallel connection, the amount of resistance is lower. Production of electricity. In our houses, we use electricity to do one or two things. So, how is this electricity we use in our house generated? Electricity can be generated through different means. One of the means is chemical. The regular battery, the battery of your phones, the battery you use in your touchlight, in your flashlights, yes, they contain chemicals, and it's even the car battery. It contains certain chemicals, and this is a way of producing electric current to power up whatever thing we need to use it for. Another means of producing electricity is via mechanical means. Our electric generator is a mechanical device. Even the electricity being supplied to us at our homes come from the dams, and these use mechanical applications such as dynamos. Even your bicycle, when you ride your bicycle, some of us will have bicycles which have flashlights. When we start pedaling, the flashlight comes on. Yes, the dynamo is a mechanical device. The turning of your bicycle pedal propels the dynamo, which in turn produces the electricity we see. Another means of producing electricity is solar. Photoelectric cells are kept in solar panels, and these capture the ray of light from the sun, producing electricity from this ray of light. Another means for producing electricity is through heat. Yes, heat in this case does not work the way the generator works because you see the exhaust of a generator. No. Rather, heat here is as a thermocouple. A thermocouple has two ends, a cold point and an hot point. Now, connecting these 2 points together induces the flow of charge within the conductor. Electric cell. A cell is a chemical compound, a chemical substance rather. It's a chemical machine that produces electricity. Your cell, especially your secondary cells, do contain, that's the cell of your car batteries, they do contain tetraoxosulfate 6 acids and magnesium and zinc rods. Now, this using a kind of electrolytic process induce charges to move from one point to another. Thereby, those charges are turned into current. Of course, remember, current is the time rate of flow of charge within a conductor. Now, there are two types of cells. We have the primary cells and the secondary cells. A primary cell, also known as a voltaic cell, contains that's a zinc copper cell. It contains copper rods and zinc plates. Now, and both of them are immersed in dilute tetraoxosulfate 6 acid. Now, when the copper rod and the zinc plates are connected to a wire, the zinc slowly dissolves the tetraoxosulfate 6 acid, and the copper serves as the anode, while the zinc starts as the cathode. And as time goes on, the battery is burnt out because the tetraoxosulfate 6 acid loses its potential. The hydrogen in it is being taken out. The electrolytic process is being completed. So in the primary cells, basically, it is non-rechargeable. It can be exhausted. But the secondary cells, which can actually be recharged, contain 2 lead rods in tetraoxosulfate 6 acids. Now, as this process is going on, it depreciates slower than the primary cell rather, but it can also be recharged. When current is being passed into one of the lead rods, it recharges the system. So whatever is lost can be replaced. That's basically the difference between the primary cell and the secondary cell. The primary cells are like your normal batteries you put in your flashlight, while your secondary cells are rechargeable batteries, as ones in your mobile phones. Arrangement of cells and circuits. We talked about cells as chemical machines that produce electricity. While some can be recharged, some cannot. But if you look at your battery, you notice that your battery has two ends. That's your normal battery that you put in your radio, your torchlight, your flashlights. You see it has two ends, the positive and the negative side, the end. Now, for your circuits to work effectively and for there to be connection, smooth connection, the positive end of one battery should be connected to the negative end of the other battery. So in your circuits, we always have, that's the circuit, the part of it that indicates your cells. We always have something like this. A single cell is represented as this, where the longer is the positive and the shorter is the negative. So when we are saying this kind of diagram, it's suggesting we have your positive, the negative, the positive, the negative, positive, negative, positive, negative, as that. So this is how the cells should be arranged in a circuit. If they are arranged in another direction, it simply in this kind of connection, it shows that the summative, that's the addition of all the cells, each of the cells, is the amount of electricity made available to the circuit. But when you are having a system as this, it means there is going to be a contradiction. That is, there will be subtraction. There will be. It means the total amount of electricity available to the system would be the difference of what is available in each of the cells. Also, it is good to also note that cells can also be connected both in series and in parallel. Yes, just like our resistors. Now, the diagram shown earlier was the connection of cells in series. Here I have 3 cells connected in series. I could also have my 3 cells connected in parallel. And what does this imply? When my cells are connected in series, the amount of voltage supplied through these cells is increased, because our voltage increases. That's the potential difference. It increases when connected in series. So if I should have say a 5 volts, each of the cells is 5 volts, a total of 15 volts is what I would have from here. But when they are connected in parallel, the voltage remains the same, unless you have different voltages, and special calculations are required for that. But at this level, you would always be given the same voltage if you are required to connect in parallel. Now, why do we connect our system to have in parallel connection? Why do we connect our cells in a parallel connection? When you connect any system in parallel, you have the chance of increasing the current that comes out of it. When you are working in series, your current remains the same. So let's say I have a particular, each of my cell is 5 volts, 3 amperes. In this particular connection, I'll have 15 volts and 3 amperes. But in this particular connection, I'll have 5 volts, 9 amperes. So this is what connection in series and connection in parallel. These are the differences that they make in arrangement of cells and circuits. So let's take a question on series connection and parallel connection of cells. Now, the first question we'll be taking is on series connection. That is a 2-in-1 question that's covering both series and parallel connection. So it's 2 torchlight batteries having EMF 1.5 volts and internal resistance of 1 ohm are connected to a resistor of 5 ohms. Calculate the currents in the resistors if the cells are connected in firstly series, then parallel. So I'll quickly draw the first one. That's the series. Since it is series connection, what we expect to see is something like now in each of the cells there is internal resistance. So the internal resistance is connected in series as well. Since the cells are connected in series, thus the internal resistance are also connected together in series with the already existing resistance in the circuit. So you can actually, if you want to depict this, we can redepict it as something like these are resistor. Inside this we have an internal resistance. Inside this we have another internal resistance. So it's all connected in series. Since it's all connected in series, the total resistance can be calculated, and also the voltage is also connected in series, so the total voltage can also be calculated. Total voltage would be 1.5 plus 1.5, which would give us 3 volts. Total resistance would be R plus, let me call this R1 and R2. R1 and R2. R1 and R2 are the same. So that will give us 5 plus 1 plus 1, which equals 7. So the total current flowing through would equal V over R, which is 3 divided by 7. That will give 0.46, 0.43 amperes. Now, in a parallel connection, it would the diagram won't look like that. It will look a bit different. What would it look like? In a parallel connection, it will look different. What would it look like? Yes, we would have our circuit. Or let me start with the resistor up. Our resistor will be there. And then which means here we'll have an R, that's R1, we'll have another R, which is R2. Now, R1 and R2 are in parallel connection with each other, but they are in a series connection with our big R. They are in a parallel connection with each other, but in a series connection with the big R. Thus, of course, as earlier said, when 2 voltages are connected together, or more than 1 voltage is connected, and it is in parallel, the amount of voltage is equal to just one of the voltages. So the voltage that will come out of this will simply be 1.5 volts. So our total voltage is 1.5 volts. And our resistance, let's start from the internal resistance. Total internal resistance will be 1 over total internal resistance over 1 over 1. So when we add this, we get 2 over 1. So our internal resistance will be equal to 1/2, which is 0.5 ohms. So our complete resistance, our total resistance, will be R plus RT, which would give us 5 plus 0.5, which equals 5 plus 5.5 ohms. And we can go ahead and calculate our current. And that will give us 0.27 amperes. Electrical energy and power. So how do we know how much of energy is being used in a system, in an electrical system? Of course, we know what work is, we know what energy is, and energy and work are very interrelated, and we also know what power is. But in every electrical system, the first thing that you can always easily calculate is the electrical power. And why is that so? Because the formula for electrical power is IV. Electrical power is IV. If we remember how we defined electric current and how we defined electric voltage, that is potential difference, then you see the reason why our electric power is IV. How did we define current? We said current is the time rate of flow of charge, and we give the expression I equals Q/T. Then we said voltage is the work done when a charge passes through a system. So we said V equals to energy over Q, or let's say work now. So when we relate this together, what we have, our IV will be equal to Q/T multiplied by W/Q. Q will cancel out and leave us IV would be W/T. And when we define what is power, we define power as the time rate of change of work. That is, the amount of work expended per time. So that's power is work per time. That's how we get watts out of joules. So to get electrical work, and that is exactly what we're looking at right now. So we can also, from this formula, we can get our work done or energy to be equal to IVT, where I is our electric current, V is the electric voltage or potential difference, and T is the time. Let's take a question to see. Let's take this question on electrical power. We have this question that says an electric bulb is labeled 250 volts and 60 watts. How much current? Let's take this question. An electric bulb is labeled 240 volts and 60 watts. How much current is taken by the bulb? Okay, the first thing to do as usual is to write out our parameters. And what are our parameters? We have voltage, which is 240 volts. We also have our power, 60 watts. Of course, watts suggests that we're talking about power. So what are our chances? What formula can we possibly use? There are 3 formulas we can use to tackle the issue of power, and all of them can be developed out of each other based on the Ohm's law. The first one is the one I earlier stated. That's P equals IV. Now, in cases where we don't have I or you don't have V, you should be able to improvise and put in your R to augment for it, for the lack of I or lack of V. So let's consider a case where there is no I. So if there is no I, then we can go back to our Ohm's law and recall, what does Ohm's law state? Ohm's law says V equals to IR. So I will be equal to V over R. So we can simply replace our I here with V over R, so which would be V multiplied by V over R, which is V squared over R. And in the case where there is no V also, that would also mean P equals IV. Where there is no V, V equals to IR, so that would mean I multiplied by IR, which will give us I squared R. So we have three formulas now that we can always consider. So we've gotten three formulas out of our singular formula now. The first one being P equals to IV, the next one being P equals to V squared over R, and the third one P equals to I squared R. So we'll come back to our question on the board. We're asked to calculate how much current is being taken by the bulb, how much current is being pulled in by the bulb. To calculate that, we just use the formula that contains current and what we have, voltage. That's the first question, the first formula. So it means P equals to IV, and from that we can calculate, we can substitute our values. That's 60 watts rather, multiply equals to I multiplied by 240. When you divide through by 240, I would equal 0.25 amperes. Let's take another question. Using this diagram on the board, we have 4 cells, 2 connected in series, 2 connected in parallel, and then connected in series with the parallel and the series connection. And we're told to neglect internal resistance. We're given a resistor here 6 ohms, and we're told to calculate the current that will be measured at the ammeter. Okay, let's start. The first thing to do is I always like to solve from the hard part first, that is resolving this EMFs. We're told that all our resistance, all our voltage, that is all our EMFs or potential differences, are 2 volts. So I'd like to resolve this one first. Since both of them are in parallel, it automatically means both of them will give us just 2 volts in this particular location. So if you wish, you could redraw the diagram and have just, instead of putting both of them, just put one of them and move on. It's as good as what you have on the board right now. So I know these two will give me, the entire structure will give me 2 volts, and this is 2 volts, this is another 2 volts. So I can calculate my total voltage to be equal to 2 plus 2 plus 2, which equals 6 volts. And I have my resistance given to me to be equal to 6 ohms. So I can calculate my current. Current equals to V over R, which equals 6 divided by 6. That gives me 1 ampere. Let's make it a little more technical. Let's calculate the power used up in this process. To calculate the power, we have 3 formulas we can possibly use. Power equals to IV, power equals to V squared over R, power equals to I squared R. Now, working with what we're given, what we have in the question, we have T and we have our R. So it will be preferred to use power equals to V squared R instead of using I that we calculated. So that says power equals to V squared over R, which says what our total V is 6 volts. That's 6 squared over 6. 6 squared is 36 divided by 6, which gives us 6 watts. So if you try any other formula, you would get the same answer. If you try I squared R, 1 squared, that's 1, multiplied by 6, which is our R, to give you 6 watts. If you try IV to get you the same answer, 1 times voltage, which is 6, is also 6 watts. In this topic, we've spoken about current electricity. We defined what current is as the time rate of flow of charge. We also defined voltage, which can also be described as potential difference, as the amount of work done when a charge flows through a circuit. We also defined resistance as any opposition to the flow of currents in a circuit. We also looked at the Ohm's law. The Ohm's law states that when current is flowing through a conductor or a circuit, the potential difference, that is the voltage drop, is directly proportional to the current flowing. And that led us to the formula V equals to IR. We considered resistance in series. When resistance are connected in series, you add them all up. And when resistance are connected in parallel, you add their reciprocals to get the reciprocal of their total. We also talked about electric cells, where we mentioned primary and secondary cells. Primary cells are non-rechargeable, while secondary cells are rechargeable. We talked about the production of currents, which we mentioned 4 different processes that we can use. We can use the chemical process from chemical energy, as in batteries. We can use mechanical process, that's using mechanical energies, as in our hydroelectric power supplies, our generators. We can use solar energy using solar panels, and we can also use heat energy using thermocouples. We talked about arrangement of cells, that is series and parallel arrangement of cells. And finally, we talked about electrical power and energy. Talked about electrical power and energy. And there we came up with a formula for P. We said P equals to IV, or P equals to V squared over R, or P equals to I squared R. And we said that work is equal to P times time, that's PT, that's power multiplied by time. So whichever formula of power you're using, just multiply with time and you'd have your answer. In a few seconds, some questions will pop up on your screen. Please attempt them, and if there is anything you do not understand, you can go over this video one more time.